Synchronous dynamic circuit techniques. Having examined the basic concepts associated with temporary storage of logic levels in capacitive circuit nodes, we now turn our attention to digital circuit design techniques which take advantage of this simple yet effective principle. In the following, we will investigate different examples of synchronous dynamic circuits implemented using depletion load, NMOS, enhancement load, NMOS, and CMOS building blocks. And the dynamic pass transistor circuits. Consider the generalized view of a multi-stage synchronous circuit shown in figure. The circuit consists of cascaded combinational logic stages which are interconnected through NMOS pass transistors. All inputs of each combinational logic block are driven by a single clock signal. Individual input capacitances are not shown in this figure for simplicity, but the operation of the circuit obviously depends on temporary charge storage in the parasitic input capacitance. To drive the pass transistors in this system, two non-overlapping clock signals phi 1 and phi 2 are used. The non-overlapping property of the clock signals guarantees that at any given time point one of the two clock signals can be active, as illustrated in figure. When clock phi 1 is active, the input levels of stage 1 and also of stage 3 are applied through the pass transistors, while the input capacitances of stage 2 retain their previously set logic levels during the next phase. When clock phi 2 is active, the input levels of stage 2 will be applied through the pass transistors, while the input capacitances of stage 1 and stage 3 retain their logic levels. This allows us to incorporate the simple dynamic memory function at each stage input, and at the same time to facilitate synchronous operation by controlling the signal flow in the circuit using two periodic clock signals. This signal timing scheme is also called two-phase clocking and is one of the most widely used timing strategies. By introducing two-phase clocking scheme, we have not made any specific assumptions about the internal structure of the combinational logic stages. It will be seen that depletion load, NMOS, enhancement load, NMOS or CMOS logic circuits. Figure: multi-stage pass transistor logic driven by two non-overlapping clocks. Figure: non-overlapping clock signals used for two-phase synchronous operation. Figure: three stages of a depletion load NMOS dynamic shift register circuit driven with two-phase clocking can be used for implementing the combinational logic. Figure shows a depletion load dynamic shift register circuit in which the input data are inverted once the transferred or shifted into the stage during each clock phase. The operation of the shift register is as follows. During the active phase of phi 1, the input voltage level Vin is transferred into the input capacitance Cin1. Thus, the valid output voltage level of the first stage is determined as the inverse of the current input during the cycle. When phi 2 becomes active during the next phase, the output voltage level of the first stage is transferred into the second stage input capacitance C2, and the valid output voltage level of the second stage is determined. During the active phi 2 phase, the first stage input capacitance continues to retain its previous level via charge storage. When phi 1 becomes active, again the original data hit return into the resistor during the previous cycle is transferred into the third stage, and the first stage can now accept the next data bit. In this circuit, the maximum clock frequency is determined by the signal propagation delay through one inverter stage. 1/2 period of the clock signal must be long enough to allow the input capacitance Cin to charge up or down and the logic level to propagate to the output by charging Cout. Also notice that the logic high input level of each inverter stage in this circuit is one threshold voltage lower than the power supply voltage level. The same operation principle used in the simple shift register circuit can easily be extended to synchronous complex logic. Figures show a two-stage circuit example implemented using completion load and MOS complex logic gates in. As you can see in this figure, a two-stage synchronous complex logic circuit example. In this circuit figure, depletion load and MOS implementation of synchronous complex logic. In this figure, enhancement of logic dynamic shift register ratio logic. A complex logic circuit such as the one shown in figure, we see that the signal propagation delay of each stage may be different. Thus, in order to guarantee that correct logic levels are propagated during each active clock cycle, the half period length of the clock signal must be longer than the largest single stage signal propagation delay found in the circuit. Now consider a different implementation of the simple shift register circuit using enhancement load and MOS inverters. One important difference is that instead of biasing load transistors with a constant gate voltage, we apply the clock signal to the gate of the load transistor as well. It can be shown that the power dissipation and the silicon area can be reduced significantly by using this dynamic clocked load approach. Two variants of the dynamic enhancement load shift register will be examined in the following, which both of which are driven by two non-overlapping clock signals. Figure shows the first implementation first implementation, where each stage the input pass transistor and the load transistors are driven by opposite clock phases phi 1 and phi 2. When phi 1 is active and the input clock and the input level and the input voltage level Vin is transferred to the first stage input capacitance Cin1 through the pass transistor. In this phase, the enhancement type NMOS load transistor of the first stage inverter is not active yet. During the next phase, active phi 2, the load transistor is turned on since the input logic level is still being preserved in scene 1. Through the pass transistor. In this phase, the enhancement type NMOS load transistor of the first stage inverter is not active yet. During the next phase, active phi 2, the load transistor is turned on since the active logic level is still being preserved in scene 1. The output of the first inverter stage attains its valid logic, which allows this newly determined output level to be transferred into the input capacitance Cin 2 of the second stage. When clock phi 1 becomes active again, the valid output level across Cout2 is determined and transferred into Cin3. Also, a new output level can be accepted pipelined into Cin1 during this phase. In this circuit, the valid low output voltage level VOL of each stage is strictly determined by the driver to load ratio. Hence, the output pass transistor input pass transistor of the next stage turns on in phase with the load transistor. Therefore, this circuit arrangement is also called ratio dynamic logic. This basic operation principle can obviously be extended to arbitrary complex logic as shown in figure. Since the power supply current flows only when the load devices are activated by the clock signal. The overall power consumption of the dynamic enhancement load logic is generally lower than for depletion load and MOS logic. Here you can see the figure. General circuit structure ratioed synchronous dynamic logic. Here you can see the figure. Enhancement load dynamic shift register ratioed logic. Consider the second dynamic enhancement load shift register implementation where each stage the input pass transistor and the load transistor are driven by the same clock phase. When phi 1 is active, the input voltage level Vin is transferred into the first stage input capacitance Cin1 through the pass transistor. Note that at some time the enhancement type NMOS load transistor of the first stage inverter is active. Therefore, the output of the first inverter stage attains its valid logic level. During the next phase, active phi 2, the input pass transistor of the next stage is turned on and the logic level is referred on to the next stage. Here we have to consider two cases as follows. If the output level across Cout1 is logic high at the end of the active phi 1 phase, this voltage level is referred to as C into via charge sharing over the pass transistor during the active phi 2 phase. Note that the logic high level at the output node is subject to threshold voltage drop, that is, it is one threshold voltage lower than the power supply voltage. To correctly transfer a logic high level after charge sharing, the ratio of capacitors C out C in must be made large enough during charge design. Here in this figure, it's general circuit structure of ratioless synchronous dynamic logic. If on the other hand the output level of the first stage is logic low at the end of the active phi 1 phase, then the output capacitor Cout1 will be completely drained to a voltage of VOL equal to 0 volts. When phi 1 turns off, this can be achieved because a logic high level is being stored in the input capacitance C1. In this case, which forces the driver transistor to remain in condition. Obviously, the logic low level of VOL equals 0 volts is also referred into the next stage via the pass transistor during the active phi 2 phase. When clock phi 1 becomes active again, the valid output level across Cout2 is determined and transferred into Cn3. Also, new input level can be accepted into Cn1 during this phase. Since the valid logic level of VOL equal to 0 volts and can be achieved regardless of the driver to load ratio, this circuit arrangement is called ratioless dynamic logic. The basic operation principle can be extended to arbitrary complex logic as shown in figure. Thank you.